Hey, good evening, everybody. Let me just first hit on the record. Okay, so good evening. Let's get started with our CS47 study. Uh, so today's topic was more like starting the computer organization, the lecture 2. Let me hear if you guys have any questions for that or previous lectures or anything else.
Yeah. So about the operation for write after read, saying that there had to be like some sort of delay in the cycle.
Okay, Brian, that's an excellent question. So I was planning to anyway explain on that topic. So yeah, just hold on to that. Uh, Anything else from anyone? All right. So okay, let me then go into like one discussion, which basically uh, try to give you an overview of the interaction between the processor and the memory, and in conjunction to that, I'll also try to describe the timing diagram, how to interpret it, what to draw, things like that. Remember, we started with the timing diagram last day on board, and explained how the timing diagram works. Now let's see how can we make a timing diagram for interaction between processor and the memory. Okay, and there hopefully I would answer Brian's query on that back-to-back read-write operation and why it need to incur one delay. All right, so let me first share my screen. Okay, share. Right now. Okay, so basically what is happening here in this picture, I just picked some photograph from internet, and one is a photograph of a MIPS processor. The processor will be studying in this class. This is one of the implementation of the MIPS processor, and a picture of a memory card. Like probably some of you have experienced when you want to extend the memory or increase the memory of your laptop. You need to open some back of your cover and replace one card with another. This is that same memory card, a 32 GB memory card. What I'm trying to explain to you here, if you look at these individual electrical pins, like this, there are a lot of pins sticking out from this microchip, this processor chip. Each of them represents a single bit information. Okay, so a presence of voltage in this pin is assumed to be 1 and absence is assumed to be 0. Thus, at this end as well, this is the memory card. Each of these individual pin, if you can see them, uh, it's basically it represents one single bit, logical bit. Absence of voltage is 0. Presence of voltage is 1. And on board, when they put on the motherboard inside the computer, connection is established. A lot of small wire like gold wire or copper wire are connected between those pins, and that's how they carry information from one end to another. So on this wire, if the voltage is present, again that represents the logical bit 1, and if there is no voltage, it represents logical bit 0. Now, of course, in our study, we won't be dealing with the picture. This is just to give you a relation with the real world. But what we'll be dealing is with something called schematic diagram. So we represent this whole setup with respect to some neat and nice picture, where let's say we call one simple rectangular box, we name it a MIPS, other box is a memory, and then instead of drawing this whole lot of pins, we mark its pins purpose, like we just name the pin. For example, ADDR31, it's kind of give you a sense that it is for the address bit 31. If it is a 32-bit system, all the memory addresses will be represented with 32 bits, and these are the individual pins that represent those bits. Okay, and similar to the data pin as well, 32-bit data, and 32 pins are there, electrical pins are there. We just mark them with a name. And there is these two other signal, control signal, read and write. They are also individual bits, and we mark them. Okay. So on the memory side, we also mark all the pins with the names. And then we make a straight one-line connection. So one single line represents one single bit in the system. So address 31 bit is connected to the memory's address 31 bit. Address 30 bit of MIPS connected to the memory's 30 bit of the address. Now you see these individual bits in the address, it does not carry almost any information. It is just a bare 0 and 1. But together, this address, this 32-bit together, they carry information. They mean something. They means, okay, processor is trying to access such index in the memory. Remember that index storage discussion last day we made. It represents that index value. Okay, so together this 32-bit makes or carries some information. Similar with the data. Individual data bit does not mean anything. It is just a 0 and 1. It doesn't carry that much information. But together, 32-bit, they can carry enormous number of information. It is 2 to the power 32 number of information, different information they can carry with 32 bits. So that's why what we can do, we can simplify this schematic diagram by clubbing these groups of bits together, which group carries an information meaning. Okay, we don't group, for example, read write together. It doesn't make sense because individually read and write, these are the control signal. One single bit is sufficient to represent the information. For example, if this read bit is set to 0 and write bit is set to 1, that means the MIPS processor is trying to write into the memory. Okay, so that's why they're not like clubbed together, but we club together this address and data. They are individually clubbed together and represented as a very simplified diagram. Here we call them ADDR with one single line and a slant straight line with marking a number 32. So this means this is a group of bits. ADDR is a group of bits. It's a group of 32 bits. Okay. And sometimes we call it a bus. So if you ever have heard the term bus, like address bus, data bus, the control bus, etc., it all means that it is a group of individual electrical signals or group of individual bits that together they carry information. Any question at this point? Okay, so far so good. Now, this system is actually missing one component. Remember, we talked about the clock systems and why they're important. They're important to give the time reference to different computing component. So here, let's put them. And I'm just replacing the MIPS with the generic term microprocessor. Never mind there. So we place a clock system which supplies the clock signal, ever changing 0 and 1 within a constant time period, with a constant timing. It gives that signal to both microprocessor and the memory. So we introduce that. And now let's try to understand some of the operations and interaction between microprocessor and memory. So let's say we start at time 0, okay? And we try to, at that time point, we try to note down the logic values of these different signals. So clock, let's say they're at logic value of 0. Just I'm using red color to represent 0 and green color to represent logic 1. All right. So clock is 0, read is 0, write is 0. And at this point, address and data, they actually doesn't matter. That's why I put something called XXX here. Means I don't care about this data, so they are marked as a black. Like this is not relevant at this time point. All right. Now, from here, let's step into the next time point, T1. Okay. So now it is after a certain interval, this logic value, let's say they get changed. Clock goes to 1, write goes to 1, read goes to 0. So that's what being reflected into this corresponding signal field in the timing diagram. So write goes to 1, read stays at 0, clock goes to 1. And in the address, microprocessor provides a value 12, let's say, and on data it provide a value 15, let's say. So that's what being changed from a dashed line, which is kind of don't care. Now at this point, address is having a concrete value of 12 and data is having concrete value of 15. And at this point, T1, what processor is trying to do is basically do this thing, write 15 at address 12. Okay, that's why it actually produces that time address of 12, data of 15. And you notice this is I just change it to the blue line, meaning some meaningful data is being carried into. And there is a direction sense, like the information is flowing from this side to this side. So all the information, see, from the clock to the memory, clock to the microprocessor, read and write both from microprocessor to the memory, data is from microprocessor to the memory, and address is from microprocessor to the memory. So far, so good. Question at this point? All right, now let's move forward. Let's see what happens to the T2. Time T2, this is like equal, this spacing is equal. The time difference between T1 and T0 is equal to time difference between T2 and T1. Just don't go with the diagram. In diagram, you will see this is a little bit narrow and this is a little bit wider. Don't pay attention to that detail. But our assumption, this interval is basically a constant interval. So T1 minus T0 is same as T2 minus T1 in this scenario. Now at this point, your clock goes to 0, read and write does not change, your data and address bus value does not change. So nothing is happening. Usually in the digital system, at this time point, T2, where some clock logic goes from high to low, usually nothing happens in the digital system at this point. Our happening age is only when the clock goes from low to high. So this part is called a rising edge of the clock, and this part is called a falling edge of the clock. So digital system, most of the time, interesting things happens during the rising edge of the clock. All right. So now let's move forward to T3, which would be the next rising edge of the clock, right? So next rising edge of the clock, what happens at that time point, your previous data, this 15 at address 12 is actually registered in the memory. So memory takes complete one clock cycle, one rising edge to the another rising edge to complete the requested operation. And that request came in at the T1, this rising edge from the processor. It is asking the memory to write the data 15 onto the address 12. And at the T3 time point, memory completes that operation. So that's one write clock cycle. So write cycle 1. And at this point, T3, microprocessor wants to do another write 41 to the 29 address. So what it does, it basically keeps the write signal on, read signal off, sends a value, bit combination, bit pattern combination that represent 29, and data bit pattern combination that represent 41 at this point. So things repeats like this, just like the previous one. Next, the falling edge T4, nothing interesting happens. And T5, memory completes its operation, 41 at 29, it stores that value. And now at this point, processor wants to read from address 12. Okay, that's what the processor wants to do at this point. So how it does, clock edge become like positive edge, write, it goes to the lower logic from 1 to 0, read jumps up from 0 to 1, address value changed to 12. On the data side, see, this is, I marked as a black because at this point, I really don't care about the data. It's of no significance. Nothing important is going on in this line. So it is marked as black. Now next, down clock cycle, these things, logic stays as it is. Nothing interesting happens in the lower edge, falling edge of the clock. And then next, right, upper edge, high edge. Now memory completes the reading from the memory. It means it's fetch or restored those value from the memory storage and sends the data towards the microprocessor. So look at the arrow of this data line now, and is sending the data over there at the T7 time point. So T7 time point, two things is happening in simultaneously. One, processor is sending a read request 29 to the memory. See, it changes the address to the 29. It's keeping the write to logic 0, keeping the read to high. That means it is sending a read request to the memory to read from address 29. At the same time, your memory is sending back the data 15 to the microprocessor. Okay. Now, this is very important concept to actually grasp. Like it is not really a serial thing that is going on in the hardware scape. It is practically a parallel phenomena going on at the same time point. Now, going forward from there, next clock edge, nothing interesting happens. But remember, this data is being present already to the microprocessor. Question is when microprocessor is going to process it or consume it, as we call it. It's basically the next clock edge. Let's assume it is microprocessor can consume that data in one clock cycle. So when it is being present to the microprocessor, it needs to be there on the data line till the next rising edge of the clock cycle to make sure that data 15, remember like this was 15 being sent over here. Now that data 15 came over, consumed inside the microprocessor at that time point. And that time point, multiple things are happening. One is your processor is sending a read request from the address 12. So it is presenting an address 12 to the memory, keeping the read as high, write as low, and the address is 12. And other phenomenon in parallel is happening. Memory is sending the data 41 to the processor at this T9, which is result of the read request sent at T7. Like T7 read at 29, 29 had a value of 41. It is being sent, so T7 request being completed and the data being sent on the T9 at this time point. And on top of that, processor processed the data for operation at T5. This 15 is came into the processor is doing something with that. Okay, so that's not important what it is doing, but important is microprocessor is consuming that data at the same time point. Now going forward, next clock cycle, low, it doesn't matter. And then it will come to high. Before go to that phase, let me point you out one thing. Look at this read cycle. Your memory is completing operation in one cycle. Okay, write cycle is one cycle, it done. Other cycle, it is done in one clock cycle. Now read operation by itself is done by the memory in one clock cycle. So it is request came in T5. It is done that reading in T7. It is only at this point, memory is sending the data out into the data bus. And T9, it is that data being consumed at the microprocessor. So this whole time is called a read cycle. So read cycle is longer than the write cycle because the data being produced to be consumed by the microprocessor. We need to consider that as well. However, the memory takes the same amount of cycle to complete the operation. Write takes one cycle, read also takes one cycle. It's only that we need to let microprocessor consume that data. We need to add one more cycle to the read on top of the read cycle. So read cycle become 2 cycles long. All right, question till this point.
Yeah, I have a question. So you know how you said that the processor and the memory kind of can do two things at once, or two instructions, separate instructions at the same time. Is that an example of parallelism?
At the hardware bit level, yes, this is information are being processed in parallel, but not really from a high level programming perspective. That concept is a little bit different.
Okay. Okay, yeah, thank you.
All right. Now let's move forward to an interesting story about this T11. Be very mindful about this phenomenon now, okay? All right, now T11, let's say we are trying processor, so read cycle 2 is done, okay? 41 came over here. Now at this point, let's say the microprocessor is trying to make a write 48 at 25, address 25 at this point, okay? Now what is happening at this point other than this instruction to be gone into the memory or sent to the memory? Number one, your processor is processing data from the operation T7. This is, see that previous operation 41. Now it is being consumed here inside microprocessor. Memory is sending the data for the operation T9. So T9, at the T9, memory was requested to send a data from address 12, which is 15. 15 is being sent over the data line, right? So it is being sent over the data line. and microprocessor is wishing to send an instruction at the same time of write 48 at 25. Now, how we can do that is simply set the read signal to low, write signal to high, address to 25, data to 48. Now, bum. It's the same electrical line, right? We don't have extra line to send that 48 data over to the memory. I hope all of you agree on that. So that means it cannot be done. It's absolutely impossible to initiate a write operation into the T11 because simply that line being busy from to carry the data from memory to the microprocessor, right? So what do we need to do? Let's step back. Okay, let's step back to T9. Okay, T9 operation and T10, step back one step. What we all need to do if we need to issue a write operation at this point, we need to do nothing at this point. Let it just complete those operations. Let microprocessor consume the data, let memory complete sending the data over to the microprocessor, and then after that, that's a T12. No, nothing interesting happens. At T13, when my read cycle 3 is done, at that point, your 15 is already came over to the microprocessor. It is being processed, and microprocessor can reuse the data line to send data 48 back to the memory along with the address 25. So at this point, write operation is possible. So that's what happening. Now read is 0, write set to 1. And before that, if you look at this one, what we did is we can keep the read and write signal to 0, which means no operation. Basically, we're not doing anything. And then next cycle, we go with the write operation with 25 and 48 being written onto the data address and data bus respectively. And then next cycle, T14, let's say this is nothing is happening there. And a next positive clock cycle, your 48, that value is written at the address 25. And after that, let's say I don't care, so I do put a dotted line for data and address. But two things, or a couple of things you need to now see here. See, we can do in the successive positive edges, okay, we can do back-to-back write. We can do back-to-back write and read, right? Means like previous operation was write, next operation is read. We can do in the next clock cycle. And back-to-back read is also possible, but back-to-back read-write is not possible, simply this phenomenon. That's why we need to place a one cycle gap there. Just to make sure you know what I mean by the cycle is basically one positive edge to another positive edge is called one clock cycle. Okay, so back-to-back operation in successive clock cycle. That's what I mean. This from one positive edge to the another positive edge. That's called one complete clock cycle. And also another thing you need to, hopefully it is now clear, if you now look at the timing diagram, how to reimagine what was happening from the beginning of the time till the end of the time in this timing diagram, right? It is just an aftermath of what is physically happening in the system in the temporal line or timeline. Basically, that's what being captured in terms of logical values of this digital signal. Brian, is that clear now to you why it needed an extra cycle?
Yeah, I think it makes more sense.
All right. Any other question from anyone? Okay. So let's see. 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 Let All right, so now, what's the time? 6:30. Okay, let me pull out my poll. Let me see your preparedness. Class preparedness. All right, let's take a few seconds to complete this poll and let me see where you are. All right, I think all of you have participated already. Let's end the poll, share the result. Let's see. Have you watched your lecture videos and read lecture notes for today's topic? 50% of you said yes, all of them. That's very good. Thank you very much. That's the way you need to study in this course. None of them, I am hoping that person doesn't have that access to the lecture notes and videos, or lecture notes and videos on the Canvas. By the way, you can access all of them, all the videos on my YouTube channel. Okay, it is there. You can just lecture from lecture 1 till everything is there, so you can watch them if you don't yet access to the Canvas. And for the materials, if you don't have access, please send me email. I can share those Google documents with you. And others, please keep up the pace. Please make sure you actually complete the reviews before you come to the class. It is very much possible that if you start falling behind, it will be too late to catch up with the class. Okay, this is a very high-paced, very intense class. Make sure you are on top of the everyday's topic. About the queries, corresponding discussion pages, 3 of you said yes, and 54% says I don't have a question. 35% said no. That means possibly you have questions, but you haven't put it in the discussion page. Let me go back to the discussion page and see if I have missed anything on your queries. Hey, why don't I see any module 1 QA? You guys said, at least 3 of you said you have a query and you have already noted that in that corresponding discussion page. I don't see any on the module 1 query. Okay, anyway, so keep those questions coming. Keep those questions coming and make sure that discussion pages are live and everyone jumps to the discussion. I hope so. That's how we can engage ourselves onto this course. Okay, let me stop sharing the result. Now what next? Okay, why don't we take 5-minute break at this point, and 6:40 we'll be back. Okay, let's get back to our business. Our break is over. Now, let me give you an overview of what is coming up in the next lecture and what is to be expected. Okay, so this is your course module that you are going to, we are actually going through the basic computer organization. And then the last lecture is on number representation. So this lecture is about that this group of bits, what information or what value they can represent. Remember, just we talked about this address bus and data bus, and this address bus and data bus can actually represent the values together, this bit combination together. This is more like a mathematical foundation of what they can represent, what is the limitation of their representation. Just like remember, like in a computing system, in a computer program, you cannot represent arbitrarily any number in the world. Like there is a limitation, there is a range that you can represent in a high level, like variable, like say it is a integer type or long integer or float. There is a limitation, system limitation, that which values, lower limit and upper limit, that you can use and you can represent. So this is more like that theoretical foundation, this chapter, that how the values are represented and what is the ranges and how we can convert from one value system to another. So three value systems are basically of our interest. One is the decimal number system, which is we all used to, we use everyday purpose, decimal number system. And then the binary number system, which is being used in the computing system. Remember this bit, this is full form is bits, it's binary digit. It's short form, binary digit short form is bit. And this binary digit is only 0 and 1. And how you can combine them, multiple number of bits together to represent the value. So that's the discussion here. And another important representation is the hexadecimal number system, and which is quite useful in the computing system study, in the sense that even though the computer system, the electronic system itself represents all the value using the binary number system or Boolean numbers system, or these bits, using the bits, we often represent for human consumption purpose those values in the hex. And there is a reason for that, why we don't like to represent numbers in a decimal, in a computation world, especially related to the hardware world, but we love the hexadecimal number system more than decimal number system. This study tries to explain that as well, and also give you the steps and process to convert one system to another, like from binary number system to the decimal number system, to and fro, and from decimal to hexadecimal, to and fro, and binary to hexadecimal, to and fro, how we can manage it. And also see, there is this reference to the chapter by this reference textbook. If you are interested, you can go for like more deeper study into those chapters. But to grasp the overall concept, I believe this note is sufficient. Now let's go through what is there. Like we study about the integer representation and study about different number systems and the base notation, what they mean, and then some like one slider to explain the whole steps in the conversion process, one system to another. Okay, and then we take the route of examples like decimal to binary conversion, the steps, and there is two different methods we can actually follow. to do it. And then we talk about decimal to hex conversion in the similar way, hex to decimal conversion, and then we go with this binary to hex conversion, hex to binary and vice versa. Without computing anything, how we can actually manage to convert them. That's the discussion topics here. And the negative number representation, oh, this is a very important concept. You need to actually pay more attention here to know how the negative numbers, especially the negative integer numbers, are represented in the computing system using 2's complement form. It is very, very important to understand, because we'll use this concept later in building up the arithmetic logic unit. Especially the adder, subtractor logic circuit will be using this concept very much. So very important. Please pay attention to these representation as well. And we also discuss about the ranges of different number system and what not. I think these are the all things that covers it. And this has about like 4 videos, 16-minute average time each videos. So please make sure you plan ahead on watching this and complete that before the next class on the next Tuesday, coming Tuesday. Question? All right, now let's do one small problem. How about that? Let me share a screen. Okay. Now this is a schematic diagram problem. And if you you can also go to that class whiteboard at the Jamboard, Google Jamboard. You can also access that as well. So this one, something like this. Okay, this one. What it says, it's a, let's say, 24-bit ALU. Can I bold? Anyway, it's a 24-bit ALU, has 2 operands, OP1 and OP2, and 2 outputs. Okay, V1 and V2. So the important part is it's a 24-bit ALU, has 2 operands, OP1, OP2, and 2 output, V1, V2. It supports 12 operations and then encoded as an input OPRN. So another input port is the OPRN. You need to draw that schematic diagram for the ALU. Now let's take like maybe about 5 minutes or a little more, 5 minutes. 6:55 will reconcile, and I'd encourage you to draw something using your like software document or diagram drawing software, so that you can share with us on screen. I will turn on the screen share and you can share your solution if you like to the class. So let's take about 5 minutes. 6:55 will be joining back. All right. Any volunteer for explaining, solving this problem? Show us. What did you do? No one?
I guess I could try.
Sure.
Yeah, let me. I used MS Paint to use my geometry diagram, but I think it looks pretty clean.
It doesn't. I don't expect anything like a Da Vinci standard or Van Gogh standard art.
So yeah, so it's a 24-bit ALU,
Mhm.
and there's two operations that go into it, and there's an OPRN with 12 different operations. So if I do recall, that should have 12 bits going in. And I think each operation 1 and 2 also have 24 bits because the width of the ALU is 24. But for V1 and V2, I don't know if those should be split to 12 instead, or they should be kept at 24.
They are kept at 24 because it sets two outputs. So that means it's a 24 bit. Operand 1, operand 2 are 24 bit, and you're correct in that direction of the buses and the notation of the buses. It's a pretty neat diagram. Why did you put 12 in the operation?
It's because in the problem it said there's 12 different operations we could do, and each operation would be 1 bit.
Okay. So that's a valid point, definitely, but not an optimal point. Like, you do not need actually 12 bit to represent 12 different operations. You can do that, of course, like each of the bit that you proposed, each of the bit is representing one of the operations, so 12 bit. But it is not needed in the sense, let's say, if I want you to design or describe an ALU which has like 128 different operations, are you going to spend like 120 bits for that? Remember, each bit is one electrical line,
That's
right?
true. Yeah.
And that means each bit actually physically costs some material. It's either gold lining or a copper lining or other things, right? So more number of bits you have, your design is costlier, basically. Okay.
Yeah.
So our target would be to lower down the number of bits as much as possible. So now this problem become like this, like I have 12 operation. What is the minimum number of bits I need to represent 12 things? Okay. And that question will be actually coming from your next chapter study, the number system study, that how many bits you need to represent 12 things. Short answer is a log base 2 of 12. Okay. So log base 2 of 12 give you 4. So that's what you need. Exactly, log base 12 is 4. You take a ceiling value of that. By the log base 12 is basically 3 point something, but we go with the ceiling value of log base 12, which is 4, and that many bits we need for the operation bus. So can you change that 12 to now 4?
Yeah.
That would be our optimal solution. Exactly. Yeah. Thank you very much. So others question. This is very interesting, and thank you, Brian, for presenting this, and you deserve a clap from all of us.
Thank you.
Any question from others? All right, Brian, you can stop sharing. Okay, then if we don't have any question, then let us stop tonight here. And please make sure you go through the next chapter before coming to next class. And we'll try to keep our discussion interesting around that topics and other topics that it may occur. And I expect many questions from all of you. All right. Good night, everybody, and have a very nice weekend.